In this video, we take a look at a Taylor polynomial that is commonly constructed for the natural logarithm function. Here we have the general formula for a Taylor polynomial. Yes, it looks very complicated, but there is a pattern to it. You need to have some number in the domain of your function where you hope to build this polynomial. For the natural log today, we're going to choose to build the polynomial at x equals 1. So everywhere you see the letter C, we will substitute a 1 in here. So we'll have f of 1, f prime of 1, f double prime of 1, etc. And then each one of these binomials will look like x minus 1. Before we get started, here is a natural log graph and a few fun facts about the natural log. Remember, natural log is a logarithm that uses the base e. E is a constant in mathematics, an irrational number approximately equal to 2.72. You cannot take a natural log of 0, but you can certainly take a limit as x approaches 0 from the right. And from this picture, it looks pretty clear that that natural log is going to negative infinity. Everybody needs to know the natural log of 1 is 0, and that the natural log of e is 1. And finally, this statement says that as x goes to infinity, the natural log increases without bound. So to build this Taylor polynomial, once we've decided to do this at x equals 1, and there's no rule that says we have to do it here, each one of these binomials, as I mentioned, is going to look like x minus 1, or x minus 1 squared, or x minus 1 cubed. So the tricky part is, how do you get these coefficients? Okay, well, there's a formula for each one. You just have to evaluate, for example, for the constant term, evaluate the function at 1. That turns out to be 0, and that ends up being our first coefficient. To get the coefficient of the linear term, just take natural log, take its derivative, which is 1 over x, evaluate it at 1, and you get 1. So that's going to be the coefficient of the linear term. So we'll have 0, we'll have 1. For the quadratic term, just go to the second derivative. Here it is. Plug in a 1, and you get negative 1. But the quadratic coefficient is not negative 1, it's negative 1 divided by 2. Because you have to divide, starting with the quadratic term, by 2 factorial. Let's take a look at the third coefficient here. It's actually the fourth. But for the cubic coefficient, we get to the third derivative, which is 2 over x cubed. We plug in a 1, and we get 2. What happens when you divide 2 by 3 factorial? Well, 2 divided by 3 factorial looks something like this, where all the factors down here cancel except for the 3. So this is the coefficient for the cubic term, and there won't be a factorial in it. And you'll see that a couple times more here. The quartic term with its coefficient is computed like this. Take the fourth derivative, evaluate it at 1, you get negative 6. And then divide negative 6 by 4 factorial. Okay, negative 6 is negative 1 times 2 times 3. That's one way to write it. And 4 factorial is 1 times 2 times 3 times 4. So just as in the previous coefficient, we get lots of cancellation of factors, and the only factor that survives here is the 4. So whereas the general coefficient looks like you have to divide by 4 factorial, for the natural log, its coefficient here is not going to have the factorial in it, and that coefficient will be negative 1/4. And I think you get the idea. So let's take a look at the result. Remember, the constant term was 0, so you don't see a constant term here. The linear coefficient was 1, and that one's completely optional. And then for the rest of these just look like a half and a third and a fourth and so forth. And the terms alternate in sign, positive, then negative, then positive, then negative, etc. So that's about all you need to know. You can use this to approximate values of natural log. For example, if you don't know the natural log of 1, you can just plug 1 into all these terms, and you will get the answer 0, as you should. If you want to know the natural log of 1.5, just plug in 1.5 here and here. and here, and hopefully use some technology to help you compute that answer. There are numbers, though, it turns out that you cannot plug in or should not plug in. For example, we don't have a natural log for 0, so don't plug 0 into this. And don't plug negative numbers in. We don't take natural logs of negative numbers. But it turns out also that numbers larger than 2 will get you in trouble. So I went ahead and built a 21st degree. That's right, it had a binomial with the 21st power, polynomial for the natural log. And it had great fidelity with the natural log up until we got to x equals 2. And then all of a sudden, the 21st degree polynomial just ran away from the curve. So I tried a 22nd degree Taylor polynomial for natural log. It did the same thing, but this time it ran away in that direction. So why is it that you can't plug in numbers bigger than 2? Well, my students haven't done much with convergence or divergence yet, but let's just take a quick look. Take a number larger than 2, such as 3, and plug it in here. Well, 3 minus 1, 3 minus 1 squared. These are all going to be 2's, 2 squared, 2 to the third, and so forth. And so what you'd get, if you did this, and you shouldn't, but you'd get 2 minus 1 half. 3 minus 1 is 2 squared. Then you get plus 1 third. 3 minus 1 is 2 cubed. Minus 1 fourth times 2 to the fourth, and you see the pattern. Well, the idea here is that the absolute value of the nth term will look something like this. Let's see, the absolute value of the nth term is going to be 1 over n times 2 to the n power. And if you apply the divergence test to this and take the nth term as n goes to infinity, you'd have limit as n goes to infinity of 2 to the n over n. And then you can use an order of magnitude argument to show that this goes to infinity. Or if you don't know that argument, apply L'Hopital's rule, because this is an infinity over infinity form, and take the derivative on top, which is natural log 2 times 2 to the n, and then take the derivative on the bottom, which is 1, and then apply the limit as n goes to infinity to that, and pretty clearly that term is infinite. And it certainly isn't 0. So by the divergence test, and by the way, the argument we just made here would apply to any number that you plug in here that's larger than 2. Because when you plug a number in here that's bigger than 2, the difference is larger than 1. And so that ratio, or excuse me, that divergence test is going to give you an infinite limit. And so by that, you can know that the polynomial evaluated at a number bigger than 2 is going to diverge. That's about all I have to say. Have a good day. Goodbye.